Okay, so hello and welcome to this discussion on fluid mechanics. So, firstly, I request all of you to just go down to the first slide that is kept before this video. So, the slide is all about the features of this video, and it says that whether you should attend, spend your time in this lecture or discussion or not. Okay, so now let me tell you briefly that what I am going to deliver you. Okay, so I am currently MTech student studying in IIT Kharagpur. Okay, and I have cracked GATE 2023 during during my fourth year of my bachelor course BE in Jadavpur University. Okay, and I have cracked GATE with AIR 31 in GATE ME Mechanical Engineering paper, as well as with AIR 94 in XE. Okay, so I will share you my understanding and how we should see all the concepts of fluid mechanics and all other subjects. And I should say that this point of view is can change. Okay, so I will share my experience and my understanding of the concepts of fluid mechanics that has helped me in cracking gate as well as the semester examination. I will make separate videos about how to make your own strategy. Yes, that is correct. That is, there is no strategy that fits to all. Okay, so you have to create your own schedule, own strategy, and crack the examinations. Okay, so very few things are actually common between two aspirants of gate. Okay, of any other examination and any other fact in life. Okay, so now let us start the understanding of the fluid world. Okay, so if now I so firstly I have these two words. Okay, fluid and mechanics. Okay, so we will try to go step by step so that we will try to think very logically. That is, okay, we want to find something, and to find that we have to go logic by logic. Okay, that is first this, then I am facing some problems, so to solve these problems what should I do. Okay, so then so we'll proceed like that. So firstly we have the word fluid. Okay, so what do you mean by a fluid? Okay, what do you mean by a fluid? Okay, so sorry. Then so we can think that any material, okay, have various phases, right? That is solid, liquid, and gas. Am I right? Obviously there can be phases like semi-solid also, but broadly these three phases. Okay, so in this point I would like to say that just apply your intuition. So you don't need mathematics or any complex formula to tell that whether this material is in its solid phase or liquid phase, right? Just by seeing or touching you can say. So this type of intuitions and daily life feelings can be applied in your gate problem solving. Okay, so and also for answering surface questions. Not always you should think about that if it is logical or not. I mean, obviously, uh, it should be logical, But the things, but some things, like if you are not feeling well, should anyone say you by logic that okay, this much is your pain, and that is why you are not feeling well? You know that is some pain or some irritation is happening in your body. Okay, and that you can feel. So these types of common sense and intuition should be applied in studying anything, be it science, history, geography, anything. Okay, so first of all, uh, and I will apply these the I will apply these types of intuitions uh, in front of you step by step. Okay, so first of all, how can we differentiate? So then our next question comes there, that how to differentiate. Okay, okay. So you can differentiate it like that. That is, if I have a floor, okay, if I have a floor, and then I'm having a piece of block, sorry, then I'm having a piece of block on that. Okay, and the floor is having mu not equal to 0, that is the floor is not smooth. So this is a piece of block. Then you are applying some force on it, may it be shear force or may it be the normal force. So in this case I am applying some shear force. So will the block move instantaneously? I mean, in that instant, uh, will the block move? I think no, right? Because here we will have the friction offered by the floor. Okay, but after some time, even if the block is not moving, then also we can have the deformed position of the block like this, right? The deformed position, and this angle alpha, this is also alpha. The measurement of this angle can give us the shear strain, right? But think of that will any infinitesimally small force will be able to move the molecules of the solid? Okay, so any infinitesimally small f is enough for deformation? This question I want you to ask yourself. We will try to answer this later. Just think by your intuition. I am saying again and again. Okay, so again, and the situation 2 is we are having this floor again. Now in this case, we are having a chunk of fluid, and now by the intuition, actually you know that this fluid cannot attain a specific uh, shape like this cuboid, right? This you know by your intuition. Okay, a semi-fluid or a semi-solid can attain, but generally a fluid that we see in our life, those fluid cannot attain this type of generic shapes. So if this is a fluid, okay, now again you are applying some force, okay, Fs. So let us say this is Fs2 for case 2 and this is Fs1 for case 1. Okay, so this should be also Fs1 in the question. And now for this, the question should be reframed like this, and the same question actually, the same question. So this is actually Fs1, Fs1 or Fs2. Okay. So just think, if you can put your finger like this, then you can put your finger from this end to this end by deforming. And if you are putting if you are putting your finger from end A to end B, you have to deform or displace the molecule of this substance called fluid. But can you move your finger from this end to this end? Very easily, very easily. From this end to this end, can you move your finger very easily for this solid case? Not, right? So then, here our observation of of a very scientific experiment suggests that this must have a finite value, right? But this can be infinitesimally small. Almost negligible force is required to put your finger from A to B for the liquid case, right? Okay, sorry. So now, so this can lead to the definition of the fluid. Okay, so then if we have to define the fluid, so it is the phase, right, of a material, right? Don't mug up, just see and write what you understand in your own language. That doesn't mind. Okay. So the phase of a material for which for which an infinitesimally writing I am writing in small abbreviations for saving time. Infinitesimally small force is enough for continuous deformation of the material, right? So this is just the result of our observation. Okay. Now, what can be the cause? The intrinsic cause is nothing but the intermolecular force, right? The intermolecular attraction force is greater. So this force, if I intermolecular, so this is for solid, this is liquid, and this is gas. Okay. And what do you mean by fluid? Any of these things, this liquid or gas, are known as fluids. Okay, are known as fluids. So there are some drastic differences between liquid and gases in terms of their properties, and that I will come later. Okay, so we have defined the term fluid. Now what about the term mechanics? So this you have studied in your 10 plus 2 level also, even in your class 10 level also. That's the secondary studies. So this is a part of science. Okay, part of science which talks about, which deals with, which deals with deals with what? The time and space coordinates and their derivatives, and in the simple language, the motion and the cause of motion, right, of any system. So here I have said two words, motion and cause of motion. So this means position, velocity, acceleration, angular position, angular velocity, angular acceleration. So these things only comprises or function of space and time coordinates. And cause of motion means, okay, cause of motion means force, torque, these things. Okay, so this we study in fluid, not, sorry, not fluid, this is the part of fluid mechanics, but in general we have the kinematics, the time and space coordinate, and this is nothing but the dynamics. Okay, so then now you have this fluid and mechanics. Now what do you mean by fluid mechanics? So we have to study the motion and the cause of motion, and related to all these things of a phase of a matter called fluid, nothing more than that. Okay, motion and cause of motion and all other consequences related to the motion and cause of motion of a phase called fluid of a material. Okay, so now how, so don't mug up these definitions. If in any scientific interview you are asked ki, what is fluid, okay, so then don't just mug up these definitions and tell the interviewer. You just give these types of example, even um, uh, even you can make your own examples to describe these things. Okay, but but they don't want you to mug up any bookish definition and tell them. Okay, just go like this. Okay, now, so why should we study fluid mechanics? Now let me be very frank. The first objective, okay, so here we'll see the objectives. Okay, objectives. Okay, so very frank, let me be very frank, that is to crack exams, right? Okay, and this is very important, very important, this is right. But other than cracking examinations, okay, you will have to be an engineer, or you will have to be, or you will have to get a job, right? And what do you do in a job field? Okay, so just think of your breath. So you have to breathe all the time to be alive. So breath comprises, or breath deals with air, which is a fluid. Think of your car. You have to pierce through the air to move through the car, and that takes power. So what should be the shape of the car? What should be the engine power to pierce through that air? Because piercing through the air in a constant velocity is not an easy task. You know that in water you can run as fast as you can on the ground. So to calculate the engine power, to calculate the shape of the car, okay, and other than these artificial machines, your own body, which is the most complicated biological machine, in that body a fluid named blood is running 24 into 7 to make you alive, to make the nutrients and the oxygen and the carbon dioxide flow to the necessary parts of your body. So that is also driven by the same fluid mechanics. So from starting with the biological systems, our own body, up to the most advanced technologies, even in your laptops, the cooling system, your laptops are cool just by the air, or even the most advanced systems can cool by the application of any other fluid, right? So these are the vastness of fluid mechanics. Everywhere there is fluid mechanics actually. Okay. So these were the objectives, but this thing is also important for your life, right? Very important. But I just want you to understand to the importance of these things, these objectives also. Okay, that is, just think that if there was nothing called fluid mechanics, there was nothing called engineering, then we were the first to invent a particular shape for a car that can minimize the resistance of the air. Okay, then you can simplify the life of uh, human. Okay, and believe me, there are various things that are yet to be discovered or yet to be invented in every field. Okay, so I have now come to the sorry I've now come to the properties of fluid. Okay, properties of fluid. What do you mean by property? Every word, in everything we have to question. What do you mean by property? It is nothing but a feature, unique to someone or something, right? Okay. So property of anything, be it a solid, a fluid, a gas, anything, we can have various properties. Like any system, in any container, you can have a volume. In any container, you have a density of that particular material. I'm just going in a arbitrary manner. What other properties you can think of? Deformability. Just intuitively think what can be the properties. I mean, at this point of your education, I don't have to tell or officially define you the volume, right? And you are also thinking that I don't have to tell you about the density also. But I think, at least to some of you, I have to tell you the concept of density for the fluids, in a very uh, deep fashion. Okay. The- and there can be various other properties also that I will take step by step in a chronological order. Okay, so volume, you all know, the space occupied, right? So, but now let's come to the density. Density. Now you will jump up and say that I know that what is density is nothing but mass per unit volume. Okay, so so now I should tell you something, that is, in fluid mechanics, this V actually represents the velocity. So I will use a cut in V to represent volume now onwards. Okay, okay. So this is mass per unit volume. Fine. So now let me give you the example of two things. Just answer through your intuition. That is, what do you feel? Okay, what do you feel? Just answer by that. Okay, so this is system 1 and this is system 2. Okay, system 1 and 2 having same volume, V cut, same volume. Okay, having same volume. So the system 1 is having filled with water. Okay, filled with water, and system 2 is filled with some balloons. Okay, so these are balloons. Sorry, just think of it, these are balloons. Okay, now can you define the term density for these two systems? Again, he will jump up and he will say that this will be the mass of the water by the volume of, okay, by the volume V, and rho 2 will be the, okay, just think of the balloons. So let us say the mass of each balloon is m, and there are n number of balloons, so m into n by rho. Okay, okay, I agree with you. Now you take a chunk, you take a chunk like this in this system also and in this system also. Okay, you take the same volume of the chunk, and the volumes are, if we cut dash, here also if we cut dash. Okay, so now just this is the for the whole system, and this is for the chunk. So now rho 1 will be, let us say the mass is also m dash H2O and the V cut chunk, and here rho 2 will be for the chunk. We can see this molecule and this molecule, so two molecules, so 2m by V dash, right? Again I agree, but now let me wait for some time, and let us say after some few minutes I am again I am again giving you the task of calculating the volume of this chunk at t plus del t, and this was at time t. Fine. Again you will say that is this and this. But now let us say that after the time t plus del t, these two balls have moved from here to here and here. These two. So this is possible or not? I think this is possible, right? Then this row 2, okay, I think I should write a superscript of del t to avoid the ambiguity. This is 0 by this equal to 0. Okay, so then for, and this del t is very small, very small, and no other force or any external effect or any external effect is applied. So this movement of balloons are the properties of their own, that is because of their sorry, that is because of their um, internal collisions and all. Okay, so if just after a few seconds that the difference in density becomes so large, that is, this is a finite value, this is a finite value, and and this is 0, and this is 0. So if after a particular very small time this difference in density becomes very large, then how can you define the density of this kind of system? And we also see that for this kind of systems the density remains same, the density remains same. Okay, so the formula rho equals to m by v, the formula rho equals to m by v is applicable for system 1 but not applicable for system 2, right? Now someone tell me why it is so, and before that someone tell me the basic difference of this system and this system by your intuition. What can you see, what can you feel? Okay, so I am sure that you can think that is, this is a continuous system, a very important word in the world of fluid mechanics. Continuous system, right? And this is a discrete system, right? So these two are very important words in the world of fluid mechanics. Okay, that is, you can count the number of balloons in the system 2 but you can't count the number of molecules of water in system 1. This is another concept. So what do you mean by continuity or continuousness or continuum of a system? Any property, it should be same all over the system. Okay, So again, it boils down to the uh, kind of homogeneous thing, but it is not like that, uh, the concept of homogeneity, but it is something that is to define the density. If we can approach the system from a bulk point of view, that is, for this whole system, the molecules are spaced so closely that the properties doesn't much vary with the choice of the chunk. But in this case, the particles of the system are not so closely spaced that the properties may vary. Okay, so then first of all, to apply, so now to apply to apply rho equals to m by v. Okay, we need we have to check if the system is continuous or not. Okay, again just focus on the word continuous. So how can we measure this term? Let us say continuity. I shouldn't say continuity because continuity is an official term in fluid mechanics, so I will say continuousness. Okay, I don't know if the English is correct or not. Okay, let us say continuousness. How can we measure that? How to measure? So now again, just think again two cases. Okay, and this time also we have, let us say, molecules like this, and in this case we have the molecules like this. Okay, so here's the case 1, this is the case 2. What do you think if I want to measure the continuousness of 1 and continuousness of 2? By your intuition, continuousness of 1 is greater than continuousness of 2, right? Because the molecules are closely spaced. The things are continued. The things are continued. So here we can say that the okay, we can say that the intermolecular space, let's say here small I of 1, and here it is small I of 2. So small I of 1 is much lesser than small I of 2, the intermolecular space. Okay, so we can measure the continuousness by measuring the intermolecular distance. But now the problem arises, if you measure it for the solid, it can be possible because the relative motion of the particles of a solid is negligible. There are very small vibrations. But in case of fluids, that is for solids and gases, there are intermolecular, sorry, there are, I mean, motions. The molecules of a fluid or a solid or a gas are always in motion. So how can you measure the intermolecular distance? Because in the next moment it is subjected to be changed. Okay, so this is the problem 1. measuring the small I for fluid. Okay, problems for fluid. Okay, problems for fluid. And the problem 2 is, okay, you can compare this continuousness for two systems, but now if you have to take the decision, taking the decision for one system, okay, then how you can take the decision? So these are the two problems. So let us attack the problems one by one. So for this problem, we have something called mean free path, mean free path, or lambda. Okay, mean free path or lambda, right? So this is nothing but the mean path that is covered by uh, two molecules between the two successive collisions. This so this thing we have studied in our 10 plus 2 level also. The path covered in between two successive collisions. So again apply your intuition and say me and tell me that is molecule 1 and this molecule 2, if they had to collide by this distance, and if they had to collide by this distance, the mean free path lambda 2 is greater than lambda 1. So the mean free path is a measure of the distance, or a delegatory of the term small I. Okay, so this small I can be replaced by this lambda. Fine. Okay, so problem 1 can be solved because we have the defined quantity mean free path. So this concept has saved us. Now how can we attack the problem number 2? So here for comparison we had, okay, we had this I, right? But now for lambda, so again take the system 2, again take the system 2, okay, again take the system 2, and if now I compare this I2 with the length of this square or this cube L, so this I2 by L, so this I2 by L and I1 by L, let us say I1 by L. So again this is the thing. So this I by L can also be a measure of the continuousness, that is, in language, how closely the molecules are placed compared to the length scale of the system. Okay, so I have coined up a new term, length scale, right? Length scale. What do you mean by that? Length scale should be that scale or the characteristic length scale. Okay, should be that scale up on which the properties or the property of your observation, okay, the property in which you are interested is changing, that is your characteristic length scale. Okay, characteristic length scale, mind it. Okay, so this length scale or characteristic length scale should be defined by you. For a pipe, it can be a diameter. Okay, for a sphere, it can be the diameter or even the radius. Okay, for a parallelepiped, it can be any one of the side. Okay, so this ratio of the I, intermolecular distance, and the length scale can be a measurable parameter to define or to judge the continuousness. Okay, so and for the problem 1, we can't take this I, so we have to go for the lambda. So then this thing boils down to lambda by L. Okay, this is a very important number for the fluid mechanics and known as Knudsen number. Okay, Knudsen number. So if the Knudsen number is very high, that means lambda is much greater than L. Case 1, not so continuous. Okay, even if this lambda is comparable to L, then also this is. And if this lambda is very small compared to L, then continuous. And if the system is continuous, then we can have the luxury of applying this thing. Okay, we can have the luxury of applying this thing. Sorry. Okay, and for a infinitesimally small or the differential case, this thing. Okay, so this choice of volume is very important, for which this choice of volume should be there. So this volume should be such that this Knudsen number Kn should be less than 0.01. Okay, okay, so this is a number actually, that is uh, so here nothing is nothing is there for remembering. Okay, so this is just a concept. Okay, so this is the concept of Knudsen number, and we can have these types of systems also, where we have this molecule separately and we have to think of every molecule separately. Okay, so then we can have a microscopic approach where we have to deal with every molecule separately, and this approach, where the Knudsen number is very less, is called a macroscopic approach. Okay, so to define the density in a continuous manner, we have to go for the Knudsen number, and this thing is known as continuum hypothesis. Okay, so uh, I want to share you a message, that is, don't study like this, that I will study first continuum, then something called density, then compressibility. Actually, continuum, density, compressibility is all linked to each other. Just there should be one word, either continuum or density, and all this concept should be there in your mind. Don't mug up. Just go like this in a scientific manner. Okay. So now I will stop here for today. In the next discussion, we will carry up from here in a scientific manner, and just let me know if you have any feedback for me, that is this is wrong or bad, I don't like your way, you should change, or I am going a bit faster or a bit slower. Anything you can share with me. This is not a lecture, this is not a teaching. I am sharing my experience and concepts with you. I am discussing with you. I am eager to learn from you because I am a student and I will be a student forever. Okay, so let's continue our journey onwards, this time onwards. So, thank you.